Okay, let's go over the code and then try to see how hacking and exploiting this code works. So this is a very simple program in C. You don't really need to know any programming or any C. I'm just gonna gloss over this code with you together so that we understand what this code does, and then we'll see how it's vulnerable and how a hacker would actually hack this code. So a typical C program starts from main. This is the entry point to the code. And this particular program doesn't do much. The return 0 is the end of the program in main, and this is only calling check pass. So it's running a subprogram, a function that's called check pass. So we come up, see this is the check pass function here. This is the interesting function. We're going to go over it. And basically what it does is that it asks for your username and then asks for a pin. And the entered pin, if it's the pin that's up here or any other secret pin, it's going to call transfer money, as you see here, and transfer $1,000 to your account. So now we want to play an attacker that doesn't know this pin, but still wants to be able to transfer this money to his account. So that's the goal of this section. So let's go over the check pass function. It's a pretty straightforward function. I'm going to go over it. So the first line, we allocate some memory from the computer to username. So this is just a variable. It's 100 bytes of memory allocated for username. And the program is allocating this so that when it reads the username from the user, it can store it in this variable and then use it later. And it also has a check pin int, which it reads from the user and compares with the secret pin that we have up here. After that, the code starts by saying the printf function just outputs whatever you put in it. It says enter username and goes to a new line. And then it reads from the input that username variable. And then it says your username was whatever we entered as the username. And on the next line, it says now enter pin. Then it reads the pin. And here's the key part. So it checks whether the entered pin is the same as the secret pin. So if they're equal, it says you entered the right pin, calls transfer money, and the money gets transferred. And otherwise, it says invalid pin, bye, and the program terminates. So this is a very simple C program, as you see. The vulnerability here is that the attacker is assuming that the username will fit in 100 bytes of memory. Okay, let's go compile and run this code to make sure that it works as expected. So I'm calling the C compiler here. It doesn't really matter what I'm passing to it. It's basically a simple code compilation. Okay, so I compiled the code and now I have a binary here. That was the code and this is the binary. I'm going to run this code and you see it says enter username. I just try test and then it says your username was test, as we saw here. And then it says enter pin. I try 1, 2, 3. It says invalid pin and bye. Now I run the same program again and I try test 2 as username, but the pin number 1, 2, 3, 4, 5. And you see that it says you entered the right pin and $1,000 was transferred to your account. So this is the intended behavior of this application. Now we want to play an attacker that doesn't know the secret pin but wants to be able to hack this. Before exploiting this program, the hacker has to find the vulnerability. If the hacker has access to code, he can know that this 100 is the vulnerability here, but otherwise he can just test the code. So let's just test it. So I'm going to enter the username 12345678990. I'm going to copy this string, hit enter, enter some pin, and it will terminate. Now this time, I'm going to paste that multiple times. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then I hit enter. And you see that it still worked because it was 100 bytes so far. And I enter the pin and it terminates. Now this time I want to add it instead of 10 times, a little more because we have 100 bytes and we want to see what happens if we add some more. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And it says enter pin 1, 2, 3. And okay, so this is the interesting section here. You see that there's a segmentation fault core dumped message here. This means that the program crashed. And a crash means that the program had an error that made it terminate. So that's the interesting part. As we said before, a crash, a vulnerability might be exploitable. So this is what we need to investigate. So now to automate this process, and instead of entering it every time, I'm just going to use Python. So I'll do Python, and then inside the Python code, I'll say print a multiplied by 100, and then pipe that to the code. So it's pretty much like typing a 100 times. So Python types a 100 times for me. If you see, if I delete this part and just leave this code, hit enter, dash C here. Still space here. Okay, so you see that this Python code is just outputting 100 A's for me. And I can then pipe that into the input of code so that I don't have to copy and paste that. So the output of that Python program goes into the input of the code. And you see that it runs like I entered the username A 100 times, and it says your username was A 100 times, and the pin was not entered, so it says invalid pin and terminates. Now we're going to try the 120 here. You see that we see the segfault. So before going further, a hacker would like to know what point is exactly causing the segfault. So we know that it's somewhere between 100 and 120. So let's try 110. So it doesn't work here. Try 111. Doesn't work. Try 113. It works here. So let's try 112. And we get an interesting thing. So you see that in all cases, when I crash the application, it says segmentation fault. But in this particular case, it's saying illegal instruction because this is the edge case. This is the important case for me. This is where I want to hack the program. So we now know that we need at least 112 bytes of data to crash this application. Now, let's see and figure out what we want to do with this. A hacker would then object dump the program, the binary, into disassembly code. And then see that disassembly. So a hacker would have access to this, as you can see here. This is the disassembly. This does not include the source code. This is just the binary of that application transferred into machine language called assembly. So this is the actual code that's being run. Now we want to call this function. This is the transfer money function, as we saw before. This corresponds to this code. It has transfer money, check pass, and main. You can see this is transfer money, this is check pass, and this is main. And these numbers here are the actual machine code that gets executed. And the instructions here are the equivalent assembly code, which is a low-level language used in reverse engineering and in optimizing and operating systems and other cases, but it corresponds one-to-one directly to these machine codes. So the hacker wants to call this function, transfer money. And this is the address for that function. So let's see what the hacker does. The hacker is going to run the same Python code, and this time add the following address to it. I'm going to use this format that's going to be a little weird, but bear with me, I'll explain it in a minute. 840408 and pipe it to code. So you see now, very easily, it says $1,000 was transferred to your account. So the transfer function was called, even though we did not have the PIN and we used any username that we wanted. So this is our input. You see that it has some weird characters at the end. That's why we're using Python to generate that, because we can't manually type these characters. And the reason that this is happening is because these extra characters are going inside over this. It's called a buffer overflow. They're going over these variables and overriding the actual function. So when the function tries to work and get back to main, instead of going back to main, it calls transfer money. So this is a bug in the program, an unexpected feature that the program didn't intend, and we're using that to exploit this code. So now let's see what's the thing that we entered here. So this is the address that we wanted to go to transfer the money. It's 0804848B. It's a hexadecimal address, so each one of these digits is between 0 and 15. But because we can't write 15, 10 would be A, 11 would be B, 12 would be C, 13 would be D, 14 would be E, and 15 would be F. So you see that in all of these addresses and in all of these codes, we only see the letters A, B, C, D, E, F, and nothing else, because these are hexadecimal numbers. These are pretty much numbers that we replace with that. So this is the address, the number that we want to jump to. But the interesting thing is that the program in the actual memory stores these backwards. So each two of these is 1 byte, and it should go backwards. So we have 8B, then 84, then 04, then 08. These are the 4 byte sequences that we want to add, which is what we've done here. 8B, 84, 04, and 08 in inverse order as to here. And these \x's here simply specify to Python that this is a hexadecimal number that follows you. So Python is basically outputting the exact same thing that we have here in actual character code in this piece of code. So that's why it works, and this is replacing the return address using buffer overflow and causing the program to call the transfer money for us. And you can see again, if I run it again, I can change whatever I want here. It doesn't have to be A, it can be B, it can be whatever. Let's try X and run the same code. You see that the same thing happens. It says $1,000 was transferred to your account. And it's because the programmer assumes that there are only 100 bytes here and the username is not going to be more than 100 bytes. But an attacker can abuse that assumption and make it overflow.